Cable ABC has a length of 5 meters. Find the position X and the tension in ABC for the system to reach equilibrium. The sac has a mass of 100 kilograms. Neglect the size of the pulley B. First, we need to define the problem. We need to find the position X, and we need to find the tension ABC for the system to reach equilibrium. Then, we need to gather information. Cable ABC has a length of 5 meters. The sac has a mass of 100 kilograms. The horizontal distance from A to C is 3.5 meters. The vertical distance from A to C is 0.75 meters, and the size of pulley B is neglected.
So we used a vector model to show our equations and formulas. As you can see from the vector model, the two x components cancel out, so we can neglect them, and the y components would equal the force of gravity. This is by Newton's second law of motion. So to find the tension of the rope by T, we're going to add up all the forces, which should equal 0 since the mass is stationary. We know that the force acting on the mass would equal to its mass times acceleration, or in this case gravity, by Newton's second law of motion. So for the mass, the force acting by gravity would be 100 kilograms times g of newtons. We also know that because it's stationary, the two y components of the forces would equal that. Therefore, t sine theta plus t sine theta would equal the force of gravity. So we can find what t times sine theta would be by plugging it into the formula. And we would get t sine theta equals 490.5. We're going to use ratios to figure out what theta would be, since we know that cos theta would equal x over AB, or AB would equal x divided by cos theta. We can then also find what BC would be equal to, because we know that one of the sides of the triangle would be 3.5 minus x. So BC would equal 3.5 minus x divided by cos theta. We can then plug it back in, since we know that AB plus BC would equal ABC, or 5 meters. We do this and we find that cos of theta would equal 3.5 over 5, and then theta would equal 45.57 degrees. Now that we know what theta is equal to, we can plug it back in with t sine theta equals 490.5. Using this, we divide by sine of 45.57 and we get t is equal to 686.87 newtons. So the final answer for tension is 686.87 newtons of force.
So after we solve for tension, we're going to be able to solve for the position X to solve the problem. As you can see on the chart, we can put a point D that's in line with point A, and we can actually put a point E that's in line with point C, with both points D and E being in line with point B in a straight line. So from that, we can figure out that BE has to equal BD plus DE, and once we have that, we can figure out the next part. So as we know, BE equals BD plus DE. So from that we can figure out the equation that BE equals x times the tangent of theta plus 0.75. We can also figure out that BE equals 3.5 minus x times the tangent of theta. The reason it's 3.5 minus x is we know the total distance from A to C is 3.5, and we can subtract x, which is the distance from position A to position B, and that gives us our equation 3.5 minus x times the tangent of theta. Now we have two equations that both equal the same variable, so we can actually just set those two equations equal to each other, as you can see, which gives us x times the tangent of theta plus 0.75 equals 3.5 minus x times the tangent of theta. So from the last step, we already know the theta, so we can easily just plug that in, and when we plug that in, we get 1.02 times x plus 0.75 equals 3.574 minus 1.02 times x. And then now just doing some simple algebra, we can solve it down to where x equals 1.384. So for this problem, to find the position of x, we could have used Pythagorean theorem. We decided to go ahead and do, as you can see, the trig ratios. We just found for our group it would be easier to solve that way, but we could have used the other way too.
The answer that we found for x makes logical sense, since it is less than the distance from A to C. Our answer for tension also makes logical sense, since if you plug it back into the equation, the forces cancel out, showing that the pulley system is in equilibrium. The concept in this problem is important in the real world, since it deals with tension and forces. In dealing with things such as bridges, buildings, and elevators, it is important to account for tension and force to ensure their safety.